So today we'll talk about C++. So the idea is, of course, not to get through the whole program, because if you jump, for example, on my lecture, where is my lecture? Here, or here maybe it's simple to do. If you have a look here, it's a really long lecture, so of course we will not have time to do everything, but I will try to tell you a little story to follow all the lecture, not in detail every time, but all the lecture. And we'll start with that. And yeah, take that pretty much better. So I'll start with a little presentation, and then we will talk about some stuff. We'll get some exercise, and hopefully we will finish on time. So, as an introduction for this lecture, I try to replicate what we usually do in development. So first, before you start your project, you want normally to explore a lot of solutions, and then you pick the best solution you want, and you create your project with a nice design in mind. So we will start with function timer, how to time, what are the problems with timing, with different clocks that we can use. Then little benchmarking, what to do, not totally in detail right now, but you have the full detail in the lecture. Then we will talk about data layout, as I told you already, and Adrien also, it's really important to have performances. Then vectorization, last, we're supposed to do some vectorization, and a Laplacian approach to take some advice with Macao and how to deal with that. And after that, we'll say, okay, we are ready to do a nice implementation. And the kind of challenge of this lecture was to develop everything with one main, just to check if it's possible, and the good point if it's possible. So, so the idea is to have a main with a design, and we have interfaces, once for the argument parsing, because you know it's tedious to parse argument when you want to play with your program, so don't do that. Use a library for that. Adrien, I think we'll present that to you also on Thursday for Rust. And the same for the I/O. You don't want to struggle with I/O, so use a nice interface, and then you can change if you want. And finally, we have the computation, of course. So we have auto-vectorization backend, we have blocking, we have advanced blocking. We'll see that this afternoon with Sébastien. We have TBB backend, we have also MVC++ and CUDA backend. So we'll do we use the same design next week to do some GPU stuff. So first, let's start with an Adama project, of course, just to set the scene. So it's an element-wise operation, and we can write this as a for loop. You know the deal. And once you want to do some timing of this, you initialize table. You don't forget to freeze the table, of course, to make sure that you do not have memory problem. Then we want to call the Adama product at some point. We start a timer, we stop the timer. And of course, if the function is really simple, you don't want to call it once, but several times. You will have a certain precision, so in nanosecond or in cycle, depending on what we want to do. And we do several calls on the Adama product, and then we compute the time, the elapsed time of the computation, and we are happy or not, depending on the result, but normally this is a nice way to do it. And we compute every time the total time of the computation, because if you increase the number of elements and the total time is decreasing, normally you should have a problem. And we also compute the time per element, because it's a nice metric to have the efficiency of your computing also. And we'll play with that a lot at the end of the lecture. So let's start gently with O2 optimization, so not too much, but a bit. If I do that, if I do 10,000 tests, I get this kind of this kind of stuff, so it's a bit messy. And what we can have, we can say that, okay, the main time is here, but it's not really precise. It's a bit of a mess. And sometimes we get some accident, and the computing time is exploding. So it's quite complex to have a look here. So let's do a distribution of that. Of course, once we do a distribution of something like this, we dream about a nice distribution with nice average, nice standard deviation. So it's nice to tell your boss, okay, everything is under control, but the problem is the reality is this kind of stuff. And as Adrien will explain that to you this afternoon. Mainly, once you want to do some optimization and some timing, you will have multimodal distribution. So the point at this moment is it's not really great to have a mean, so you prefer to use a median to have a kind of representative time, and you don't really want to use standard deviation. You prefer to use quartile or decile, depending on the precision you want to have, but it will avoid this kind of weird accident that they can happen, but not too much. And maybe you want to know them, you want to diminish them, because especially if you want to do some online signal treatment, maybe sometimes you have a problem here, and this problem costs a lot, and you cannot be fast enough to retrieve all the events you lost. So you have to take care of that. So it's important to have this kind of distribution in mind. So it's not a Gaussian. That's life. We have to deal with that. So then I will briefly summarize what is vectorization. So Adrien said yesterday, so and Vincent. So the main key of vectorization is to compute several elements at the same time. So in the same cycle, basically. And on Linux, if you want to know what are your flag, what you can use, you have the proc CPU info. And on Mac, you have a system control -A, and you can have a look. So I can do the same here. See if I do the proc CPU info, you will get all these flags. And of course, if I grep...
Probably you can zoom?
Yeah, I can zoom. I can zoom like this. No, yes. Where is my mouse? Maybe a bit too much. This one. Normally should be okay. So grep AVX, and then you have the AVX flag, AVX2. You can have AVX512 if you are on the server. Normally, it's nice for you to have this kind of information in mind. Especially depending on the compiler you want to use, sometimes you have to specify the optimization flag, so -M, AVX, AVX2, AVX512. Sometimes not, because for a recent compiler, it's not mandatory every time, but sometimes you want to do that. And personally, I prefer to do it, so I remember what was the optimization in my command line, so it's nice. And so when we vectorize, so I will do this brief summary just for Macao, because there is a lot of vocabulary associated with Macao, so I will present that everything here. So let's pretend we are on AVX. So we vectorize 8 floats at the same time, so 8 float 32. And to do that, we have vector register boundaries. And if we have a line data, so we align our vectors in this kind of border, we get this kind of alignment, for example. And here, basically, we have only vectorized computation. And to simplify this slide, we will pretend that all computation costs 1 cycle. And so we have 3 cycles of computation here to do the full computation. Of course, it's a bit complex than this, but we will see that later. And then sometimes you don't have aligned data. So they are aligned on a border of a float, but not a border of a vector register. And then the compiler has to do some tricks to be sure that everything is nice. So we will start with vectorized computation, so it's nice. So if the whole computation costs 1 cycle, so we have 1/8 of a cycle for each element, AVX. And then we have to deal with the first part and the last part. So the first part is called the pill in most software and specifically in Macau. And the last one is called the tail. So these are simple loops, and the compiler will generate this loop for you to be sure that if you are using a table which is not aligned, you will consume the elements one by one until you reach an aligned border, and then you vectorize. And at the end, you stop vectorizing and you consume the last element one by one. But the problem is it's quite costly, in fact, because here you are in scalar computation, so you get 1 cycle per element. And so if you do the addition, you will have 10 cycles. So basically, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's much more than the 3 cycles as before, and we compute the same amount of elements. Of course, to try to fix that, we have a solution. We can use a padding. So you add extra element to your vector until you have a nice, you reach a border of an aligned vector. So of course, it's better to do that on an aligned vector, but here it's nice to show you that way. And the question is, yeah, but what am I supposed to put inside the padding as a value? 0, 1, none, whatever, I don't know. And of course, the answer is it depends. So for most operation, if you want to use addition, multiplication, subtraction, etc., you can put zeros because they are neutral for the operation. But of course, if you want to do division, you will have a problem. So you want to put 1. But the other part is division is quite costly, so you prefer to multiply by the invert. So then padding of 0 makes sense. But you always have to ask yourself, what are the value I want to put in my padding? And then with the padding, we can drop from 10 cycle to 8 cycle because here we are only 1. And for example, if we have an extra vector here, even if it's not complete, we finish with the padding and we go from 3 to 4 cycles. So it's nicely vectorized. So if we, yeah. Normally, you should have the mic of the Muppet Show banquet.
Un, deux, trois. Ouais. Mais il marche pas.
Yeah, it's only for the stream.
There's no on off. Okay. So I hope you hear me. 2 questions on the slide before.
Yeah.
First question, why don't you pad on the pill?
It's generally you want to align. You align your allocation so you don't have to pad on the pill. But it's also possible, yeah.
Okay.
But personally, I prefer to align my vector. It's more simple.
Okay. Second question, why do you care about the neutral values? You can't just ignore what happens here?
You can ignore, but for example, if you do some matrix product or stuff like this, at some point you will mix the padding
in
value
case of
with the real
reduction.
value.
Okay.
And here, of course, it's in a Adama product, so you don't mix, but at some point you can mix.
Okay, thanks.
Yes, Adrien?
Also, besides the reductions, you may get some fun with subnormal numbers on Intel CPUs if you don't control your padding values.
Yeah, don't spoil your presentation of Thursday. But yeah, you can struggle also with denormals and stuff like this, so you prefer to have a nice padding. So if we do that on another product, you recognize the total time on the left and the elapsed time per element on the right. And normally at this point, you are happy because you get your L1 cache, your L2 cache, and everything is nice. You have a nice step. So everything goes according to plan. But if you have less elements, what happened? Because here I start with 1,000 elements. The first point of my graph here is 1,000 elements. But if you have less, they all fit in L1 cache, but in terms of computing per element, what is the evolution of all these curves? Someone on Discord has spotted the answer. No, not yet. Okay. If I decrease the number of elements, if you remember what Adrien said yesterday with the pipelining. Yeah, but you're a teacher, so come on. No? Okay, so let's do it. You have everything in the lecture if you want to play with that in the first part of the lecture. So we will get something like this. So at this point, we have a convergence of all the performances. At this point, we can ask ourselves, what does it mean? So I voluntarily exclude the vectorized version in orange because vectorizing with one element, the processor will say to me, "Are you kidding? One element to vectorize?" But what does this value refer to? No? Not even a bit? You have a nice convergence? No, not.
Since you calculate the elapsed time per element,
Yeah.
it obviously goes down when you increase the elements into the time step.
Yeah.
Also vectorized. So, I mean, when you have constant time per one vectorized unit, if you have less elements, the time remains the same.
Yeah.
So it obviously goes down.
Yeah. You are close, but there is a point missing. There is not on Discord. Okay. So this time is the size of the pipeline length of my laptop, because I did the studies on my laptop. And if you refer to the Intel or AMD documentation, you will see that it's 14, 15 cycles, depending on your version of your processor, but it's something like this. So at the end, you have a value, and you walk down through the whole pipeline with your value, and you have to wait until the full length of the pipeline to get the result. And since you have one value, of course, it's horrible in terms of optimization because it's not designed for that. So that's why you can reverse engineer the pipeline length of your CPU with an Adama product, because the Adama product is wonderful, of course. So little reminder of the CPU pipeline, as Adrien explained to you yesterday. So we have an instruction N. So we first fetch the instruction, then we decode the instruction, then we execute the instruction, we do some memory to get the information, and then we write the result at the end. So of course, it's much more than this in the real pipeline, but it gives you a nice idea of what's going on. And of course, if I have the previous instruction, I have the pipeline here. And if I use the previous instruction for my Intel CPU at 14 stages or AMD CPU at 15 stages, we have a nice shift here, and we can perform several operations, different operations, but at the same time. And once you reach this part, your pipeline is full, and here you have a lot of performance. So you need to have enough element in your vector to have enough performance. And a nice trick to do, if you want, it's not in the slide here, but you can do the math if you want. I need to have enough element to have an efficient vectorization and an efficient pipelining. But if I have too much element, I go out of my L1 cache. And the question is, on AVX 512, what is the minimum of element to have optimal performances? And you will see that if you do the computation, that the value is really close to the full size of the L1 cache. Because, especially if you don't, if you align, you will have maximum performances. But if you don't align, the worst case is to have 15 cycles at the beginning lost and 15 cycles at the end lost. So you can compute 30 times 16 float at the same time just because of the pin and the tail. So at some points, the bigger your vector register is, the less you want to have pin and tail. Otherwise, you will kill your performances, especially if your vector are not too big. So it's always important to have that in mind. So then, so you have the best performance. I say that again, and let's talk about memory layout. So as we said yesterday, but I will do that again because it's important, in fact, in this lecture also. So once you read and write some bytes, cache line, it's about 64 bytes. And if I do an ugly structure of coefficient, about 80 bytes in this case, I will get something like this in memory. And my thread will, if I read, for example, the U value each time, I will jump in my memory and I will kill my performances because each time the processor will send me back a full cache line. I use only one element of the cache line. So that's bad because I use 4 bytes on 64 bytes. So it's really bad in terms of usage. It's quite the same if you want to go to the library and the library is 100 kilometers from you. You don't want to buy one book, to buy several because it's better in terms of cost. The same idea here. So of course, if we do some structure of arrays and not array of structure, we will have something like this. And if I want to read U, I can in two cache line here, and it's much more efficient. And all the bytes are used, so you use a full bandwidth here, and everything is efficient. And since Adrien told about that also yesterday, but it was quickly, I will do also the same with the chart. So if we want to read and write line cache, so we have this kind of data, and then we can read everyone vectorizingly or whatever, everything is nice. The processor is helping you, it's the point. And if you have several threads, if they read parts which are adjacent to each other but not the same cache line, it's okay. And of course, as Adrien said yesterday, if you want to read the same part, the threads are really polite because they cannot read and write in the same cache line, so they wait until the other did the same, and you lose a lot of time by doing that. That's why you want to parallelize by block to have one read and write in the same part for the same thread. And we will express parallelism, and then we will play a bit with the lecture because I'm particularly sure you wait for that. So the last point before the lecture. So I already presented that a lot of time, but it's really important, so I do it again. So we want to compute efficiently on CPU, on GPU, on whatever you want. So we want to express parallelism. And as Vincent said yesterday, it's not embarrassingly parallel, it's delightfully parallel, because you want to be in this case. So let's pretend I want to treat an event. And I'm really lucky because I have a lot of events to treat in an experiment, for example. And they are stochastic, so they are independent, so I have a lot of parallelism to express. If I do that, it's nice, but sometimes maybe it does not fit in my memory in terms of CPU or GPU or the size, the kind of GPU you want to use. Sometimes it's not enough. And maybe I want to start a lot of threads, and it's not possible. So I have to break down my event and to say, okay, my event, maybe they are composed of captors. So maybe pixels in that case, or it could be sensors in general. And sometimes it's not enough. So we want to break down again and say, okay, my pixel, they tell me maybe a time response. So slices, waveform, pulses, depending on what experiment you are working on, or what simulation you want to do. You can have this kind of pattern. And the question is, yes, but in which order should I store my tensor now? And for that, you have to ask yourself, what am I supposed to do with my tensor? What are the steps, the analysis steps I want to perform on them? So the first one, let's pretend it's quite common. We want to calibrate. So we have voltages as an input, and we want to convert them into number of photons, energy, whatever you want to have a nice value at the end. And let's pretend for this example that the calibration does not care of the ordering. And once I say that, I don't care of the ordering, but I have the full performances even if I change the ordering. So maybe it's a really simple captor, maybe something like this. So if the first step does not care about the ordering, let's check the second one. And the second one might be an integration. So we will sum all the slices or one pixel to get some values. So I said integration, so you have to heard reduction. And if you heard about reduction, you have to think about back dependency and all the stuff we talked about yesterday. Yeah. On Discord, there is a question. Okay. In which question expert maybe? No, 15, not 16, but you're quite close. Yeah. Yeah, did you say we can possibly lose six? It's not 16, it's 15 cycles time, because if you have one, you have 15 elements, they are not aligned, and that's the worst case in theory. Of course, the worst case is a bit better than this, but yeah. And so you have the 15 not aligned at the very beginning of your vector, your table you want to treat, and you have the 15 left at the end if you do not vectorize without padding. Yeah, 15, yeah. So that's the worst case. Of course, you don't want to be in that case, and of course, you are really unlucky if you are in that case. But the point is, the more the bigger your vector registers are, the more you want to be careful about alignment and padding. That's what the point. Okay, so reduction, yeah. So there is a reduction, so we want to sum two elements to each other, and the point is we have to wait, as I said yesterday, until the result is available. And for that, you don't want to sum this value to this value if they are adjacent in memory. So naturally, you want to say, okay, I want my contiguous data to be this one, so I can sum a full vector of pixels to a full vector on another pixel for another slices, and everything is efficient. So if I do that, I can vectorize, I can GPUify, I can also vectorize the integration well and the calibration, because the calibration does not care. So it's nice. Then the second axis will be naturally this one, because we don't want to have value too far in memory to be sure that the prefetch will be efficient and we will not have problem with the memory. or at least less problem as possible with the memory. And finally, the first axis of the tensor will be this one, and here we can parallelize where we want. So it could be on cores, on nodes, on cluster, or whatever you want. Everything will be nice. That's to remember you that computing drives data storage. If you want to store data and you don't know what you want to do with them, you will have a problem of performances, and your team in general will have a problem of performances. So you always have to ask yourself, what am I supposed to do with my data? And of course, if you have several treatments to do with your data and they are not compatible, you have to find a way or an algorithm that is less complicated and give you less penalty in terms of performances. So let's play a bit with Macao. I'm sure you want to play with Macao. So Macao is not the best program in the world because it was written for my teacher, so I don't want to be too gentle, but yeah, it's a really, really good, powerful tool. So we will play mainly with CQA, so it's Code Quality Analyzer. And the idea of this tool is to do some static analysis of your binary. So you give a binary to Macao, so compile with the compiler, and you tell Macao, okay, does the compiler did a great job on this compilation or not? So do we have nice pill or tail? Do we have a nice vectorization? Do we use well the vector register or not for which and which operation? So it's a kind of a nice one to have. I always use Macao. It's really, really powerful. So we'll play with that right now. And so the usage is quite simple, in fact. You do Macao CQA, you say, okay, I want to analyze the loop of this function. So you get the function name of the loop you want to analyze. And then you do a pass to your library or to your program if everything is encoded in your program. And Macao will tell you a bunch of stuff. So as Vincent said yesterday, you have to be prepared because Macao has always something to say and to say to you. You can improve practically everything each time. But it's really, really important and really powerful to learn also new compilers or new options that maybe you didn't heard about, or to read some documentation that you didn't think about before. So we'll start with this command. So the idea here in the story is to tell you that someone bring you a program or a full project, as my lecture, for example. You don't know what's going on, even if you have the full documentation before, but let's pretend there is no. How can you get some information? So what are the good implementation? What are the bad implementation? How I'm supposed to fix that? How do I get the information? So first we will start this Macao CQA stuff. So here in ANSI, you can jump, normally if I do it quickly, you can jump on must here. So you have your account in SSH, you can log in. So here I am already logged in. So you log with Keycloak with your SSH account. Now you should get this one. And for the satellite site, you can do the same for your favorite scheduler or your favorite images. Normally you have everything done. Everything is prepared gently. And you pick the C++ 17 2023 on CPU, and we will play with that together. Okay. So here, normally, you should get a nice code server stuff. I can remove this one. In the README, you can jump directly on the lecture here. So if you want to have a look, to get some information also, because at some point it's a kind of, you want to search information. So I will let you dig into this massive lecture to get information, because it's important to answer your question yourself. So in this program, So I'm pretty sure you are practically all familiar with CMake, but we will do that together. So I will create a build directory. That's a common way to do some CMake. Of course, you can call it whatever you want. Then I go in my build directory. I call CMake ... for the parent class. Of course, if you are in Aptainer or Docker in another part, so in I think in Toulouse you have a nice script for that, but you can start it with a bind, and you say I bind in /build, or I bind in /home/joven/ example/build, and then you can jump on it as you want, no problem. And here I can call CMake. And so I will generate all the make file, because you don't want to write a make file by hand because it's horrible. And then, yeah, Discord. Here? Maybe. I hope. No, yes, maybe. No, you don't want to zoom? No. Don't want to zoom? Never try to zoom here. Or maybe I can zoom in.
With the browser, Control plus. Control plus.
Oh, no, not this one.
No,
It's not possible to. Why? Yeah, but how I'm supposed to zoom if I not have. Nobody asked me this question. How we are supposed to zoom here?
Si tu fais CTRL plus, là, normalement, ça devrait zoomer, non? Le navigateur, il va zoomer.
It's not working with the mouse. Okay. Okay. So plus. Maybe it's a bit too much. That's okay for you?
Il y a une question pour l'accès au repo.
This repo, which repo? This one? You have everything on this page. So normally you have the link on the Discord to get your US Code School. Here you have the program, and if you get in the container list, you have all the containers, and you have all the lecture. You can get this one, and you get this. Yeah, good point, Mathis. Really good point. So, yeah, I was here. Maybe I'm an admin. So we can compile. So I will compile really quickly. So the idea is to say, okay, I don't know what this soft is supposed to do. I don't know which are the good ID, which are the bad ID. So I compile everything, and then I ask Macaro some advice. And maybe I can use this command again. So the output format HTML and output path is for to have a nice output. We will not use it in the Kubernetes, but I will show you after that what it looks like, because sometimes it's nice to have this in mind. So it could be nice to use, especially if you have complex loops with a lot of build tails or stuff like this. So, but here basically, so we have the efficient, or maybe we can do that together. Did you already try? You have a nice report. Not yet. So let's pick the O3, for example. So you don't need to put the HTML output format, or except if you are on your laptop, it would be nice if you get the example. And yeah, by the way, I forget to mention that, of course, but in the first page of my lecture, you can get correction .gz with everything. So if you want to pick that on your laptop and you prefer to play with it on your laptop, feel free to do it. It's designed for that. Okay, so let's start this version. And there you have a bunch of information and you get lost. So here, so if we have this stuff, so here we said, okay, we compile so in Ryzen, so in x86-64 architecture, so detect the architecture that we want to use, and then he said to you what is the function, where is the function. Normally you should have a line. So if you want to have a line, it's the same for all kind of debugging tools. You want to have the debugging symbols inside your binary, so they can get lost. They are not lost, and they give you the nice information. The same for GDB, the same for Valgrind. It's always better to have debugging symbols to be sure that you are checking the loop that you want. So here we can check the loop with a line. We can have the sources also. So not sure if can open this one. Oh, yeah. Nice. So if you can click on that on VS Code, I guess, and then you can get the implementation. So you can pick, okay, where is line? I think it was 77, something like this. Yeah, line 77. So I can pick the line 77. I get the line 77. I say, okay, that's my kernel, so it's the right loop. Because sometimes you have initialization loop or stuff like that, and you don't want to choose this one. You don't care. You want the other one. So always check if this is the right loop. So then, we have a bad news. We reach 4% of the peak of the computational performances. And the program is supposed to be vectorized. That's a bad news. The first bad news of the day, but not the last one, but the first one. So the Macao is capable to detect also the number of cycle per flop you can have. So it can give you, it's not really precise in terms of speed up. You can have an idea of what you can improve and what you can do. And here, Macao is telling me, okay, your loop is fully vectorized or partially vectorized. Only 38% of vector register length is used. So not that good, in fact. And he told me also that we can reduce from 24 cycle to 10 cycle per iteration, which is a lot, in fact. So we can have a 2x speed up. He can tell me also that we are using, we can change the compiler. We can use associative math to have better performances, or fast math, but maybe you don't want because you know that we will have some problem with the precision, but that's an idea. Not always a good idea, but that's an idea. And here you have something interesting. Tells me that we have inter-iteration dependency. And he's right, because here we have a sum. Of course, we have inter-iteration dependency. Because here, maybe if I can do that, here we have the first loop on the row, the second loop on the column, and here we have the stencil, the row of the stencil and the column of the stencil, and of course we do a sum. And apparently the sum was not that optimized that nice way. Can you guess why? Why the compiler is struggling to optimize my little stencil here? Yeah, I make you work today, so a lot of questions. Because it's just 2 loops. What is the problem? Well, in fact, you know that if I told you that it's just 2 loops, it's not just 2 loops, otherwise you will have a nice vectorization. So. Maybe on Discord someone picked the It depends on your project, your problem. Maybe you can, maybe you cannot. In fact, in VS Code, it's a really simple project, so if you don't want to be too precise, it's not a problem. So the answer is, look at the mess before the stencil. So this is a really generic implementation, so you can have a stencil of the size you want. 10 by 10, 15 by 16, 3 by 3, everything. And another point is there is no padding. So here you have a weird min and max computation, and you say, okay, sometimes I want to iterate on 2 rows, and sometimes on 3 because I'm inside my images, and sometimes I'm on the border, so I want to iterate only on parts. And the compiler gets lost because it's too complex. And the problem is the compiler cannot predict the size of these loops because the size of the stencil is a parameter. And you do a crazy stuff with that. In fact, I do crazy stuff with that, with the min and the max, and the compiler is lost. So the compiler say, okay, I don't know what's going on, so I do nothing. Even if I put the dash F3 vectorize, the OFAT, the fastmat, the nice dash M, AVX512, something like this. I put all the arguments, but the computing is too complex, and the compiler cannot prove that everything is going fine. So it does nothing. And normally, Macao is smart, so it can spot it. Or maybe not in this mode, but we'll see that later. Okay, so the first pick was bad, but we can try another. So here we have 4% of the peak of performances for something which is called efficient simulation. Okay, I lied. So let's pick another one, this one. We have auto-vectorization simulation image, so an auto-vectorized computation. And so you are not obliged also to use the report. I will show you that a bit later, maybe just, yeah, we have half an hour before the break. For the first time using Macao, you have a lot of information to digest, but if you get used to it, it's really powerful. So we'll have the eye to spot the right information in this output. Oh yeah, it's macOS. Yeah, I did not design the lecture to be compatible with macOS because I don't have Mac, so it's quite difficult. So if you have a Linux, it should be okay, or if you have a library compatibility with the standard library because it's supposed to be standard, or quickly you change the assert file into an assert.tl and it should be okay. But yeah, it's not. Yeah, you cannot use it on Mac. I cannot test it on Mac. So this one, yeah.
Yeah, I have a question about the line you wrote, like for example, the last one. How did you found the name that you wrote after function loops?
It's the name of the function.
Okay, so it's written in a file somewhere.
Yeah, it's in the
Okay.
file. So you get the sources. You say, okay, this function is important. It's the hotspot of my computation. I want to be sure that it's well done. And you ask Macao. And
Okay.
sometimes you can have also some trouble because especially if you have too much branching in this function, Macao will complain and say to you, okay, no, I cannot follow everything. So no, normally it's better, but if you have really a lot of branching, we said to you, no, so you have to break down your function to pieces and to have a look. But yeah, it's basically the name of the function you want to analyze. By default, it will analyze all the loop inside one function.
Okay. Yeah, I just wanted to be sure because we didn't have time to read every file, so it's hard to.
Yeah, that's why
understand the line.
I tell you a story because, of course,
Yeah.
we don't have time to pass through the 400 pages of my lecture, but the idea is to give you a nice story, and then we have all the details after that.
Yeah, thank you very much.
And maybe we can do that together. So if I jump here, I do space, so CQ, no, okay. Loops, and this one is, I don't remember, of course. Which one? Simulation image. And then it's 9. Yeah, and this one is a library. So you can also have an example. So the first one is a program, so everything is in the program. The second one is a library. It's also working, no problem. It's okay for you? Okay. So let's see what Macao will say to you. So the function is this one, the sources is here, so maybe I can do that. Okay, it's well done. So then I can have my nice. So here, everything is done the same way. You have the first function, which is initialization function. So it's a really simple design. It's a really simple backend. So VS Code initialization does the initialization, and then I got this computation here, and we'll see what is going on here. And here we will have, okay, so it's small, give me the, okay. 72% of the peak of computational performance. Why better? Not 100%, but why better? Because the loop is highly vectorized, so 98% of the vector register is used. Quite a good point. So again, here, Macao is capable to detect where are the sources. And normally, here, if I show you that, you should spot immediately what changed compared to before in the code. Okay, so here, there is no min-max. The compiler is happy. We have a padding, so we have the same computing for all the pixels inside the boundaries of the image. And here what I did is I hard-coded a stencil. It's a 3x3. The compiler can prove that we have only 3 iterations. So it can unroll well this computation. And we have less problem of back dependency because everything is unrolled. And we can vectorize better also because of this. Because the compiler now understands what we do. We can prove that the boundaries of the loop are always the same because they are hard-coded. In fact, I did 3x3, but of course you can hard-code it with the macro, with something like this, with the constexpr or something like this. But here, really simple case. And so the compiler is happier, and then it's more efficient to have the vectorization. And normally it should be okay for this one. And now it's time to get the last one. Yeah, if you have some question.
What is this vec data that you defined somewhere yourself?
Oh yeah, it's in the header, I believe. It's to have an aligned vector in fact, once you use SCD vectors, they are well designed, in fact, because you can put an allocator, a custom allocator, and send them. You are not obliged to have your own data vector to have nicely aligned data. And so if you want to have a look in the allocator, if you have specific question, we can jump into the allocator here. So the idea is to use this design to say to the vector, okay, I want you to allocate, but you allocate with an aligned values. And so I define the vec data to not having to get my vector of float of a line allocator of float too big. So nice type def. And the time you want to change and to say, okay, I want an aligned allocator, but with a padding, you can say, okay, now I want a padding. Let's use a padding. Yeah.
Yeah, so it seems like I have different reports than you because I have only 17% of vectorization.
Yeah, it depends on the CPU.
Okay, well, because it's very different because you had something like 70%, and so it's in my case it's 17, so very low vectorization. Is it well, seems strange to have such
Strange,
difference.
it depends if your CPU is really recent. The compiler may struggle a bit. Maybe you have to get the last version of the compiler, maybe G++ 14 or something like this.
Oh yeah, okay. Yeah, because it's 13th generation of Intel,
Yeah.
so maybe okay.
And maybe to show you, me, I get 50% here.
Okay.
So it's a kind of not quite recent, but not quite old CPU. It's 2 years now, 2 years old, something like that. So nice point. It's way better on this one because I think this one is a bit older than mine. So the compiler are much efficient on.
And okay, so because I'm running that in the container, so if G++ is not, well, if it's not the latest version, it can have trouble to vectorize.
Yeah, it's a 13 one.
Okay.
I think normally the 13, not the 14. So yeah, depending on the architecture, sometimes it's better, sometimes it's worse.
Okay.
That's why you have to check. Maybe if you have problem with the performance, you can check with Clang plus or with ICPX if you have an Intel CPU. Normally it should be quite efficient. That's why you always want to jungle with a lot of compiler, not to be stuck with one and the one is wrong and you say, okay, I'm stuck. No, you don't want that.
Okay. Thank you very much.
So on Discord. The loop ID meaning. Oh yeah, the loop ID is inside. It's for Macau just a way to name the loop. I think normally it's a number of the loop compared to the full number of the loop inside the file, inside the binary. So I don't really use this kind of ID. I prefer to use the debugging symbols and to have a nice line inside my sources to be sure. But that's not sure if it's normally it's related just to the idea of the loop inside the binary. Not know if Emmanuel is in the chat, but he's the developer of Macau, so he can answer way better than me. So then we have this one. Yeah, just before the break, we will do the last one. So let's try this one now. So with the Laplacian, so we do a test with the Laplacian. And the idea here, so I will show you the sources after that. But mainly the idea is to say, okay, before the two examples, I compute my Gray-Scott reaction with the two species at once. So U and V at once. In fact, we can say, okay, but I read everyone once, and I do the computing, but I have a heavier body loop. So maybe if I split and I say, okay, let's compute the Laplacian of u, and then let's compute the Laplacian of v with the same function, but in two different steps. We have a much lighter loop, and maybe the compiler can do more work on it. That's the idea of this implementation. Yeah.
About the previous one, when you decide that you work with 3x3 blocks,
Yeah.
don't you have to take into account the length of the vector word for the processor architecture that you're working on, or it's irrelevant?
No, because in this case I use them as a scalar, and I hope the compiler is able to unroll, because it's only 9 instructions at the end to do the computation. If you unroll the two loops, generally the compiler will unroll the most inner loop and not the other one. But the point is to make sure that the compiler will understand that and do it for me. And I have other version when I unroll this loop, so you don't have the two inner loops of the stencil, and then you have 9 instructions to do the computing. So the compiler is forced to do that because there is no more.
But does this mean that the vector word needs to be divisible by 9, or no? The length of the word. Like how many
no,
elements
because
can fit in
it
the
has to
vector?
be greater than 5, because I use my image, I remove the border, and I apply the stencil 3x3 on all the pixels inside. So if the image is too small, the stencil is
Yes,
out
yes.
of the border of the image. But that's only for this case. I didn't check that. It's a good point. I had to check that. Okay, so normally you know how to do it, so we'll do it. So we'll finish on time before the break. So. With check. All three? No. Is it okay for you? So. So here we have the report of Pierre. I can also jump in the sources. Please come on. Okay. So here, maybe I can present you the source. So here, so the idea is this one. Okay. So we have the here, and here, okay, 72% of the peak computational performance. So we have an equality here. So yeah, well, make this a bit shorter to save you some time. So here we check this one, and we have also 72% of the peak computational performance. So we have an equality to the one before. So which one to choose? The answer is, in Macao, you have an expert output, and we will check that right now. So if I do, I think it's a conf equal expert. No, expert, please. So here I will get the expert report. And here you get the assembler, you get the all the information here, and so it's a really long report. So you have information about the inner loop, the outer loop, the thing like that. And what we want to check is the vectorization ratios. And here we get 100%, 100%, 100% for the operation that we want, so FMA, so fuse, multiply, add, and load, store, and everything. So it's quite okay, in fact, here. And if you ask the same one on the same report on the example before, you will see that it's not in 100%. So you have much more potential by using this one and trying to do other optimization or other flags to enroll, stuff like this, than the one before. And of course, it's not in the lecture. So so if I do that quickly, so here it's 50% of peak performance, and if you check the expert report, you will see that you have a nice vectorization. I can show you before the break. If I go here, I do the report, a simple report at the beginning. So we get this kind of report with HTML, so it's nice to read. And you see, okay, you have all the loops, so you can have a lot of loops in your computing. So here we have one loop. The loop is partially vectorized as before, so 38% of vectorized register. You can have some advice if you want to do some work on to improve some stuff. Here he said to me, okay, I have problem with the stride because the loops are too complex, so the compiler cannot understand what's going on. And you have the expert table here, but for this one, it's not really good. So we'll pick the second one. The second one was this one, and here it was yeah. Here you can you have to be careful also, because the first here you see 6%, and you are afraid. You say, oh no, 6%. Yeah, but it's a pill loop. So it's not the real computation. The real computation is just after that. So this one, every time I see that, I'm afraid. I say, okay, no, everything is broken. And then I realize, okay, no, it's a pill loop. Everything is fine. So it's normal. Okay, this one? Or the elder on the on the very end of the auditorium. And then here, so 50% on my laptop, but 72 on the Ryzen. So the loop is highly vectorized, so nice point. And if we have a look here, you don't have to add the expert part. You always have the expert part. So here it's much more simpler to read normally. And then you get the vectorization ratio. So it's quite okay, but not that good. And here you have the full assembler. So sometimes, for example, if you can try in the examples to try to help the compiler. So you have your nice stencil, and you can say, okay, but my stencil is really special. Maybe in the middle of my stencil, I got a 0. And you can say, okay, I don't want to compute multiplication by 0. And the compiler will say, yeah, but you load one element and you load an element after that, but there is no load here. and the compiler will do a with stuff. You will have vectorized stuff in the beginning of your computation, vectorized stuff in the end, and you will have a really slow, call, assembler call in between, and you will kill your performances because of that. So you want to multiply by 0, it's always better. So here you have the full assembler, which is generated for all these loops. So if you want to check that you use the good vector register, that everything is fine, it's always good. And if I pick the last one, so the Laplacian here, so here we have the 55%, and then we have a tail, no, it's a pill tail, but it's after that because why not? It depends of the humor of Macau, I presume. So this one I don't care, but I want this one. And normally Macau is telling you that normally it's supposed to be neglectable compared to the main one. You understand that it's a pill or a tail computation because sometimes the compiler cannot prove that you are lying or you are nice boundaries. So here we are 99% vectorization, and in the expert part, here if we check, we have 100% every time for the efficiency, not for this one, but for the ratio in terms of computing load and store. And if we check the assembler also, we can have a look to what's going on. I think now we can have a break, and we will play again, and then we will develop some stuff together, because I'm pretty sure that you want. Now we have a lot of information, we know what is good, what is bad, so we know what to implement. And of course it's not implemented, so it will be your turn to implement that in the soft. So we can have a break, half an hour, or maybe 25 minutes because I'm late, or yeah, we can start at 11. Okay.